Hi class, so this section is 13.6. We are looking at molarity as another source of determining concentration of a solution. So molarity is moles of solute over liters of solution. Notice this is solution, this is not solvent. This is defined as the number of moles of solute per liter of solution, and it is a capital M. So how do you prepare a 1 molar solution, sodium chloride solution? So this is a very simple example of how we would prepare a 1 molar solution. We would get 1 mole of sodium chloride. 1 mole is equivalent to 58.44 grams. So we would weigh out 58.44 grams of sodium chloride. We would add it to a volumetric flask. This is a volumetric flask. This allows us to make solutions as precise as possible. They are all, this flask here, let's say, is 1 liter. They're all only specific for 1 volume. And there's a little line, and this is the line that everything is filled up to, not above it. And if you understand how to do this, it's at the bottom of a meniscus. So this will kind of concave. And when it does, you take the most bottom portion, and that's where the line will meet up. So we'll add 1 mole of sodium chloride into there, the crystals, and then we will add DI water up into the line. First of all, technically, you're supposed to only do half. Shake it, make sure that it is stirred well and it is dissolved. Then you fill it all the way up, and that will make 1 molar of a sodium chloride solution. We tend to use molarity a lot, so hopefully then you will be very comfortable with it. Let's do some examples. Calculate the molarity of a solution by putting 15.5 grams into a beaker and adding water to make 1.5 liters of sodium chloride solution. So what do we have? We have 15.5 grams of sodium chloride. We're also told that we want the solution to be 1.50 liters. So what we need to do is find the molarity. And how we do that is by using this equation. It's molarity, but with a capital M, and it's moles of solute over liters of solution. So let's plug everything in. We have our 15 grams. We cannot use grams, so if we're given grams, we have to connect it back to moles, because that's what moles is what's required for the solution. So we go through stoichiometry. 15.5 grams divided by 58.44 grams gives us 0.2652 moles of sodium chloride. There's a line underneath indicating where the sig fig ends. I always go 1 extra out and never round until the very end. Now we already have our liters of solution, so we plug this in. Moles are on top, liters on the bottom. This provides us with a 0.177 molar sodium chloride solution. Determining how many grams of sucrose are contained in 1.72 liters of 0.758 molar sucrose solution. So there's a lot of information here, and we can use molarity as a conversion as well. And in this case, it's asking for grams, which is not anywhere in the molarity equation formula, but it does have moles. And once we get to moles, we can always get to grams. So what do we need to do here? Well, we're given a volume to start with. So we're going to start with the volume, and then we're going to use the molarity as a conversion. And the liters of solution here and the liters of solution here will cancel out. That will give us our moles. From there, we can use molar mass, and that will determine how many grams we need. So the relationships here are the molarity, and it's written out as a fraction. You don't ever use it as a big M when you're doing calculations like this. And then we have our molar mass. So we plug everything in. We start with our 1.72 liters of solution, cancels out solution, leaves us moles. Next thing is to use molar mass, and moles are on the bottom, which will cancel out. Then we can use the molar mass of the grams here, and that will produce 446 grams of sucrose. I've got more problems, more examples to help you understand this. What volume in milliliters of 0.220 molar HBr solution, hydrobromic solution, is required to produce 0.0150 moles of HBr? So we are asking about volume here. So we need volume. A lot of it is meant to kind of confuse you, and chemistry is really good at writing out questions that completely confuse somebody. It's like a whole different language. You have to learn how to translate it, and the first thing you should do is pull out all the information you can, and that will get you to at least understanding hopefully some of it, and then make sure you understand what the answer is, what should be, what the volume, in this case it's asking for volume. So if it's in volume, then you need to know, is it being in liters or it's in mils? This question specifically tells you milliliters. If it's not, then you would answer in liters because it's by default of that. So here we set it up. We have 0.0150 moles. So we're going to set this one up as moles. We're going to use the molarity to cancel out the moles, leaving us with the volume. But the volume needs to be converted to mils, which is done here, and equals 68.2 mils. So a question may seem very complicated, but once you pull everything out, it really is quite simple once you understand what is being asked of it. Okay, so we've looked at molarity, but what if we wanted to look at ion concentration in molarity, in a concentration of ion concentrations from a molar solution? So if we look at a molar compound such as something like glucose, if you dissolve it in water, it will dissolve, but it will not dissociate. So it'll stay intact. So 1 molar of glucose contains 1 molar of glucose per liter of solution. That's because, again, it does not dissociate. However, when you're dealing with ions do dissociate in water. They completely separate for the most part. And what the solution, the molarity that you're given is given before the dissociation. But if you wanted to know specific the ion concentration for each ion involved in that compound, it could be different than the molarity that's given before dissociation. Let's look at an example. So say you have 1.0 molar calcium chloride solution. These are both ions. They will separate. So in this case, we need to know if the ion concentration equals the concentration of the intact compound, the ionic compound. So when we break this apart, we have 1 mole of calcium ion. There's only one of them. So this 1 mole will match this 1 mole because there's only one, even though there's a 2+ charge. That goes with the ion, not about the molarity. Here, though, we have 2 chloride ions. So that means that we have 2 moles of chloride per liter. So the ion concentration could be different than the ionic compound concentration before dissolving. So this part is to show you how to do the math to determine the ion concentration, what the molarity would be for that. And it's sometimes different than what the ionic compound is. So determine the molar concentration of sodium ion and phosphate in a 1.50 molar sodium phosphate solution. So the first thing you need to do is, we know that we have a molarity of an ionic compound, but we need to break apart the ions so we can figure out what the solution is going to be for each specific ionic concentration, meaning what is the ionic concentration for sodium, what is the ionic concentration for phosphate. So what we notice here, if we look at the intact compound, there are 3 ions for every 1 phosphate. So in that case, what it means is that the ion concentration of sodium is going to be 3 times the concentration of the phosphate. So what we do also, well, let's just jump down here. So molarity of the sodium ion, it's 3 times 1.50 molarity. So the sodium concentration is actually 4.5 molar. Even though you have a 1.5 molar sodium phosphate solution, if you're looking specifically at ions, it's 4.5 molar for sodium. Now, if we look at the phosphate, we only have 1. So 1 times 1.50 is still 1.50. So the molarity for the phosphate ion is the same as the ionic compound molarity, which is 1.50. This is not very... It may look difficult, but once you understand that you can multiply the molarity by whatever the subscript is for that compound, you have the molarity for the ionic compound. Problems with ion concentration, they will usually, there will be something indicating it's ions. So for instance, you see that these are ions here. There will be some sort of indication that that's what it's asking for. If it's not, then it will always be a molarity with the intact compound concentration.